Section 2.3 is called Transformations and Symmetry. And what we're going to take a look at in this section is how to take some of those graphs that we did last time, and instead of having to just plot points, and especially plotting 5 points, because that's what we did in most cases, being able to use some basic strategies for manipulating equations and how that affects graphs. That's what we're looking for today. So this is all about kind of graphing, all right? So taking a look then, the first thing we're going to look at is some transformations. The two transformations we're going to look at first are called translations. Okay, so translations are the idea of taking a shape or an object and simply moving it. We're going to move it with these kind of translations in one of two ways. Up and down, that's one way, or left and right, that's the other way. So technically, I guess it's 4 directions, but they're moved in 2 different methods. So a vertical translation is the first one. So this is an up and down translation. So you might be going, okay, well, how do I decide if it's up or down? And that's a very good question. So if you were looking at taking a graph, like imagine your graph of x squared, a parabola. If you took the parabola exactly like it was, I can't make a parabola perfectly with my hands, but pretend. And you just moved it up or down, okay? So you're not changing the shape, you're not changing anything except for where, we call it a vertex, we haven't done that in this class, but where the vertex is and how it goes, you know, how it opens after that, okay? It's not shifting anything else, just up and down. A vertical translation is done by having something added or subtracted to the end of the equation. So if you had a function, we'll say f of x, and you added a number on the end, that would be a vertical translation. And if the number you added is positive, it moves it up. And if it's negative, it moves it down. So if I had an example that was g of x equals x squared minus 3, how would this translate the function x squared? It would move it down 3. Everybody good with that? That's all that is. Plus or minus the number at the end moves it up or down. A horizontal translation moves something left and right, like the horizon, right? Along the horizon, along a road, okay? So we're going to either move things right or left. And the way this happens is that instead of adding or subtracting something afterwards, at the end, we do it grouped inside with x. So this looks like this. Okay, so it's sort of embedded inside with the x. And that will shift it left or right. Unfortunately, it does it backwards of what you would like for me to write down. Of course it does, right? Okay, so if the k value is negative, it moves it right. And if the k value is positive, it moves it left. Okay? So you add something that's positive, you add something that's negative. That's how I'm describing it. Okay? So, for example, if we had g of x equals, and instead of grouping the or instead of putting the minus 3 on the outside, we put minus 3 inside with x like this. How would that move this to the right 3? Okay? So it'll look just like x squared, but it'll be shifted to the right 3. All right, we have 2 more types of transformations we're going to look at. Let's do a couple of examples before we get there that are applying to these. G of x equals the absolute value of x plus 2. So this is going to look like an absolute value equation, which is what shape? A V. Okay, we're going to have a V shape. And how is it going to be translated? Up 2. This at the end tells me I'm going to move it up 2. So instead of being at the origin as my sort of my corner point, my starting point, we're going to shift that point up 2. So there's my dot. And then the absolute value equation actually moved to the right one and up one, and then to the left one and up one. Okay? And then we're going to connect those to be my V shape. How about number 2? How is this shifting this?
Right.
This will move it right 2. Again, so instead of being at the origin, I will be 2 to the right. That's my starting point. And I will go right 1 and up 1, and left 1 and up 1. And then I will connect my dots as the V shape. Really and truly, 3 points is enough to graph these. We saw that happen last time a lot, right? We were getting basic overall graphs, so we used more than 3 points. But a lot of them went left, right, up, down, 1. It was all about the number 1, wasn't it? Yeah. So these shifts don't affect that. They don't affect the left, right, up, and down 1. The next transformations will. Okay, our next set of transformations are called reflections. So if you imagine a reflection of my hand, okay? So there's 2 ways I can reflect my hand. I can reflect my hand down, right? So it looks like the hand went upside down. Like these shapes that we've been doing, the U's and the V's, they could just flip upside down. The other thing that I could do with my hand is I could flip it left and right. Agreed? Right, so sometimes we think about our 2 hands when we put them up being mirror reflections of each other, right? The outline or the shape of them anyway. So there's 2 different types of reflections. There's what's called a vertical reflection, or there's a horizontal reflection. Okay, so we'll do vertical first. So the vertical reflection would be a reflection up or down, depending on the image originally the way it was. It has another name. We'll do that in a second. The second one is a horizontal reflection, and a horizontal reflects things left, right. Okay, so another way of describing a vertical reflection, so imagine if you did this, right, where it flipped it down, is that it's a reflection over a specific axis. Which axis would it be reflecting over if we're flipping it up and down? The x-axis. So sometimes you'll also hear this called an x-axis reflection. I bring this up because I don't know why, but different things sort of hit us differently as being easier to remember or more meaningful to us. So I don't care which way you describe these. It doesn't matter to me. But I want you to have multiple ways that you could describe it, either in your head or as you're doing it, either way. And then if you reflect things, right, horizontally, you're actually reflecting it over which axis? A y-axis reflection. Now, these are actually done differently, but it's all about a negative, right? If you flipped things down, you might imagine all my positive values become negative, all my negative values become positive. So if you're doing a vertical reflection, that's the top one, what happens is you simply put a negative in front of whatever your function looked like before. I'll give you an actual example in a minute. And then, if you're doing a horizontal reflection, you put the negative inside with the x value. Now, here's something that's pretty cool. If you're doing a vertical translation, where in the world did we see the vertical translation happening? On the outside, right? Vertical stuff happens on the outside, and it happens on the outside with reflections as well. And then horizontal stuff is happening on the inside. All right, so everything that happens inside with x is a horizontal change or a transformation. So let me give you an example of each of these. An example might look like, let me see which one I wrote down earlier. F of x equals a negative square root of x, like this, where the negative is on the outside. But if you were doing it on the inside, you would get a horizontal reflection. Now, there are some graphs that you reflect them horizontally, they don't change. Think about your absolute value graph. That V graph, What if you flip it around the y-axis? It didn't change anything. Okay, so that does sometimes happen, especially with our reflections around our y-axis. Square root of x, though, doesn't have that feature. It's not symmetric. It's just sort of this one branching piece, so it reflects differently. All right, our last transformation is called a vertical stretch shrink. And again, it's almost like two of these in one. So this is all done vertically, which means where do the vertical things happen? They happen on the outside. Okay, so everything I'm going to write down is going to happen on the outside of where x is. And so we can either stretch or shrink. So I'm going to put stretch first, and I'm going to put shrink second. And even as I write shrink, I'm going to give you a more mathematical term for it because sometimes you'll hear it referred to this way. And in some ways I kind of like it better. It's called a compression. Okay, so this is all done with respect to the vertical. So if you imagine having a parabola, so just picture a parabola in your mind instead. And if you took the two ends of the parabola, the ones that point upwards, and you pulled them up, you stretched them up, the graph would look how? What would it look like compared to the original one? Give me some verbal, just descriptive words, adjectives. Skinnier. Or maybe you have this taller, narrower, right? If you pulled it up and you made it stretched out, it would actually look taller, thinner, narrower, okay? Now what happens if you imagine like Play-Doh and you squish it down, you compress it? It's going to look fatter or wider or longer horizontally, right? That's what these kinds of stretches and compressions are. They're all in relation to doing it with the vertical description. Stretch it vertically, compress it vertically. Okay? And it's done by multiplying the function by a number in front of the function. We'll put it like that. K times f of x. Okay. So if the k value is bigger than 1, then it is a stretch. Okay, so you put like a 7 in front of it, and you're going to have a really skinny parabola. But if you go and you put a value that is less than 1, and I don't mean negative, right? I'm thinking fraction kind of numbers here, because the negatives we dealt with reflections, right? You don't have to worry about the negatives. I'm talking about positive numbers. If you put like a 1/5 in front of it, you're going to be squishing it flat like a pancake, like Play-Doh, like silly putty squished, right? Okay, so a smaller value than 1. So if I had, for example, I've got 2 of them written down, so I'll write down 2 for you as well. The first one would be something like g of x equals 2x cubed would be a stretch. It would make it narrower. And if you did g of x equals 1/2 x cubed, it would be shorter, fatter, wider. All of those things would apply. You've heard the joke before that says, right, I'm not fat, I'm just vertically challenged. If you just stretch me out, I'd be perfect, right? It's the same idea kind of with this, right? Depends on the perspective. Are you talking about stretching it vertically or stretching it horizontally? Because that would actually describe it differently. We're always going to be talking about it vertically. All right, here's a couple examples then. First one, how is this going to change the absolute value graph?
It's going to be on the x, it's going to go negative, or to the left.
Nope, not going to go to the left. Good guess.
To the right.
Okay, say what you're going to say there for me, Kira.
It's going to go down.
Okay, down. What do you mean by down?
Like the V's are going to go down.
Okay, so it's going to open downward. Okay? Or you could say it's going to be flipped downward or reflected downward. Yeah, the negative is a reflection, and it will reflect downward instead. So the origin will still be our sort of starting point, and we'll still go right and left 1. But when we go right 1, we'll go down 1, and when we go left 1, we'll go down 1. So it will open downward. Okay, so that negative will be how it's opening. It's opening downward now instead. It's a reflection. Forget it. All right, how is number 4 going to change? What's that 1/3 going to do?
It's going to make it
It's
fatter.
going to make it fatter, shorter, wider, all those words, right? Now let me show you how this graphs, because that one I haven't actually shown you or thought through with you yet. Still going to be on the origin, still going to be opening up, right? Okay, so normally I would go 1 to the right and 1 up, and I'd plot a point. What I'm going to do now, is I'm going to go 1 to the right, and I'm going to go 1/3 up. That wasn't a very good 1/3, but maybe I should expand my picture just a little bit. That's not too bad. Okay, so instead of going 1 to the right and up 1, I'm going to go 1 to the right and up 1/3. I'm going to go 1 to the left and up 1/3. Now, because this is linear, right, these are actually line pieces that I'm drawing, it would actually be equivalent to going 3 to the right and up 1, 3 to the left and up 1. It only works because it's a line, but it is true that this will actually go through the value 3, 1. Look at that, just right there. You see that? Because it's lines. If we were dealing with an x² graph, that wouldn't work that way, okay? So it's more accurate, really, to say that we're going 1 to the right, 1 to the left, and up 1/3. And again, we're going up 1/3 because there's a 1/3 here, right? Okay. All right, we're going to do one more, it's a 2-part example, and then we're going to stop for today, okay? One more slide, that's what I should say. One more slide. All right, so on this one, we're not graphing, but what we're going to do is we're given some verbal language about how a graph has changed, and we're going to create the equation that goes along with that verbal language. So the first one says we have the graph of y equals x², and we're going to move it right 4 and down 7. So I'd like for us to identify, how do I make something go right 4? Okay, so I'm going to do -4. What was that you said? Somebody said it. I didn't hear. Robert, was that you? Michael? Travis, who? Inside the parentheses. So the -4 will be inside. I'll just write inside, but inside the parentheses with x. Okay, that's correct. How do I get it to go down 7? Someone besides Travis, since you got that one for us. Or say that, Kara, louder. Okay, we're going to subtract 7. We're going to do a -7 on the outside. Or you could say it's at the end of the graph, or at the end of the equation. So you can give your function a name, f of x. You could call it y equals. That's fine too. Doesn't really matter. You need to group inside with the x the -4, and then the squared is after that, okay? The squaring affects the -4 part. And then a -7 outside at the end. All right, next one. It's a square root graph, and it has 3 pieces in which, 3 ways in which it's been changed. It's stretched vertically by a factor of 4. It's reflected over the x-axis, and it's moved up 3. So we're going to do just like we did in the last one. We're going to write down what we do to get it to have that happen. How do you get it stretched vertically by a factor of 4? Okay, so the negative we'll deal with in a minute. We just need to stretch it first. Okay, so Julia, say that louder. What do you want to do? You multiply the entire function, or you could say multiply the outside, right? So, but we're going to multiply by 4. And the reason we're multiplying by 4 is because it said it's stretched, right? It's stretched by a factor of 4. So that goes together, that makes sense. And multiply on the outside, right? Because it says vertically. Okay, somebody said something about a negative. That's coming from the reflection, right? It's reflected over the x-axis. So where will the multiplying by a negative occur? Negative on the outside or inside? Outside. Good job. On the outside. And then the last thing says to move it up 3. How do you get something to move up 3? Add 3 where? On the outside or at the end. All right, so we have our function. I'll just call it y equals for this one. I have a square root of x. Nothing is supposed to be happening in the inside with x, so it's just all by itself, right? I started by saying that I needed to multiply by 4, but the 4 needs to be negative, so the negative goes in front of the 4. And then I need to add a 3 to the outside or at the end of the function. Now, how could you verify, besides checking the little, like, check my answer on my math lab, that this is correct? What could you actually do? Graph it. So most of you have graphing calculators. If you don't, and you're still doing the work on the computer anyway, there are graphing calculators within the computer, right? Online, just Google for one. Graphing calculator, put it in. Make sure that visually it did what you expected it to do.